Hi, I'm going to take the next few minutes to work through a problem that demonstrates exponential growth. I'm taking this problem from the homework set, problem number 4 in module number 7. So this problem works with doubling time, and it says the doubling time of a certain population of deer is 15 years. So that means every 15 years, no matter where we are, 15 years later, we will have twice as many deer as we had before. So let's see what that looks like. We could say that if in 2010 there were 500 deer in the woods, then since the doubling time is every 15 years, we would know that in 2025 we had 1,000 deer. 15 years later, which would be in 2040, we would have 2,000 deer. That's what that means. Every 15 years, we're going to double. The question, though, isn't asking us that. The question's saying to find by what percent does the number of deer increase each year. Well, if the population's doubling, let's say I'm going to make a table. And the table is going to be time in years and the population or the number of deer that we have. And, oh, sorry, I'm going to need a little more room than that to the right. So I'm going to get rid of all this that I have here. And I'm going to start over with the table over here. So if I have T for the number of years and P for the population, right? I have in year 0, I have some number. It doesn't even really matter what that number is. I'm just going to call it P. 1 year later, I'll have some more. 2, 3, 4, 5. I'm going to go all the way down to 15. Right? And so whatever the population is in year 0, in year 15, 15 years later, the population is going to be double that or 2 times that, which means, let me shrink this up a little bit, that from here to here, I had to multiply by 2. That's what it means to double. I'm multiplying by 2. If something is 2 times as large as it was before, that means it has a 100% increase. Right? I started with my original 100% and I added to that another 100%, which gives me a total of now 200% of the original population, which means that my change factor is 2. This is my 15-year change factor. And the 100% increase is my 15-year percent change. Okay, so let's get that terminology out of the way. That's what that's all referring to. The question wants to know, what is my 1 year percent increase or my 1 year percent change? In order to find the 1 year percent increase, let me pick a new color for my pen. In order to find the 1 year percent change, I first need to find the 1 year change factor. Well, how do I do that? Where does this 1 year change factor come from? Well, the 1 year change factor comes from the fact that if I only wanted to find out the population in the very next year, I would have to multiply P by some value, and I'm going to call that value B. I don't know what that value is. I know that if I go 15 years, I'm going to have to multiply by 2, but I don't know what it is for every 1 year. But I do know that if I took and made little individual jumps between year 0 and year 15, right? Between every single output, I would need to multiply by B over and over and over again. And you would see that I would have to take B times B times B, on and on and on, times B, until I got to 2. Right? All those little B's multiplied together would be the same thing as just multiplying by a single 2. So in other words, B to the 15th power is equal to 2. That's what this statement right here told me. That my 15-year change factor is 2 tells me that B to the 15th power is equal to 2. So now we have to do a little bit of algebra to find out then what is B. And it turns out that, we'll get a new piece of paper on here if I can. Turns out that if I have B to the 15th power equals 2, then algebraically I would raise both sides to the 1/15th power, because B to the 15th raised to the 1/15th from our rules of exponents, we know that that just gives us B to the 1 equals 2 to the 1/15th. So B is 2 to the 1/15th. All right, let's see what that approximates to. And so I'll pull up Desmos for that. And if I take 2 and raise that to the 1/15th power, I find that that is approximately then equal to 1.0473. That means that all of these little b values here are equal to 1.0743. If I take 1.0743, multiplied 15 factors of that, I would get approximately 2. So my 1-year change factor is 1.0743. Now, to go from a 1-year change factor to a 1-year percent change, you have to subtract out that original 100%, which is that 1. So let me show that over here. So I have a 1-year change factor of 1.0473. This means that each year, the output of DEER is 104.73% as much as it was the year before, which means that my 1-year percent change is the 4.73%. The 100% represents what I started with, and everything else represents my increase. So now I learned from this that the 1-year increase is 4.73%. So let me go back and fill that in here. By what percent does the number of deer increase each year? 4.73%. And how did I find that? I took the doubling time of 15 years. So 2 to the 1/15th power equals my 1-year change factor, which is 1.0473. That's my 1-year change factor. So this is my 1-year percent increase. Okay. So hopefully that is helpful. And then to find out how much the number of deer increase every 5 years, well, now I'm just saying I'm going to take that 1.0473 and apply that 5 times. Again, if I pull up my Desmos, a 1.0473, raise that to the 5th power, and I get that that is approximately equal to 1.25996. Okay, so that is approximately equal to 1.26 if I want to do that, which would then tell me that that is now my 5-year change factor. So that means the population of deer is 126% of what it was before, which means that I have a 26% increase every 5 years. Okay, a 26% increase every 5 years. Notice I couldn't just take that 100% increase that I had and divide by 15. If I do that, that's like treating it like a linear situation. This is not linear. You see that in 5 years, I have a 26% increase. That doesn't mean that in 10 years, I'll have a 52% increase. What would my 10-year increase be? Well, let's look at that. Let's bring up another sheet of paper here. Okay, the 10-year percent increase. Well, I would have to first find the 10-year change factor, which is the 1-year change factor raised to the 10th power. Pull up my Desmos here to find that out. And I get 1.5875. 1.5875, which means that my 10-year percent increase is 58.75%. Notice that's not double 26. Because we're increasing and our increase is always calculated by the previous output, as that previous output grows, the rate, the amount that's getting added on is also growing. So the rate of change is increasing, even though this multiplier is a constant.